Hello everyone and welcome back. We're on to lesson 3. Today we're going to talk about one-sided limits, we're going to talk about continuity of piecewise functions, and we're going to talk about horizontal asymptotes and the connection they have to limits with x approaching infinity. So for the first time, x will not be approaching a constant but a concept. So let's start here with one-sided limits. The notation is brand new, and notice we have limit as x approaches a with a little plus, x approaches a with a little minus. We've actually already done this. If you think back to lesson 1, when we were looking at the tables, we would look at just the numbers that were to the left of x, just the numbers that were to the right of x. We would look for those two different patterns, and based on those two patterns matching or coming together, then we'd say that the limit exists, or if they don't come together, then they don't exist. Well, that's exactly what this is. The little plus says we're approaching from the right-hand side, the left says we're approaching from the left-hand side, and then if these two match, if they're the same number, if the pattern on either side of our x value match, then the limit exists and we write that number. But if we get different numbers, like in the first lesson we had 3 for one side, 5 for the other, then of course we say the main limit does not exist. So let's look at an example of this in practice and see what we can do with it. Okay, so here's our first one. We're going to deal with an absolute value of x over x as x approaches 0. And the first thing we always want to try, we want to see if we can just input 0 right there. And if you do that, well, that turns into 0 over 0, an indeterminate form. So we can't do that. So what we'll do is we're going to try numbers first that are on the right. And so we're going to pick some x values that are on the right, and we're going to get closer and closer and closer. With our pattern of picking x values, we're going to keep picking values that are getting closer to 0. So I'm going to start out with x equals 1. And when I do that, if I plug a 1 in here, I get 1 divided by 1, that's 1. Let's try 0.5. So I plug in a 0.5, 0.5, absolute value is 0.5, divided by 0.5, it's still 1. And I'm going to keep getting closer and closer to 0. So I'm going to say x equals 0.01. When I do that, 0.01 over 0.01 is still 1. So hopefully we're starting to get the idea that as we're plugging in these numbers, there's a really strong pattern emerging. 1, 1, 1, 1, 1. Seems like this is approaching 1. And that's pretty darn close to 0. Okay? And just by inspection, we can see that whatever we plug in here, any positive number, you're going to have that positive number divided by itself. That's always going to get you 1. That's more of a way to understand it. So let's start looking, as we go through this, let's start graphing what we see. So I'm going to put 1 here, negative 1, 1, negative 1. It looks like all those values on the right are 1. And think for a second, what should be here? We can't actually plug into 0, so there's got to be a circle there. There's the first part of our graph. So as we approach, we're getting close to 1. Okay, let's look at the left-hand side. For the left-hand side, we're going to do the exact same thing, except we're going to pick numbers that are to the left of 0 over there in negative land. So here we go. I'm going to pick actually the same numbers symmetric about that point. So I'm going to have x equals negative 1, and x equals negative 0.5, and x equals negative 0.01. So here we go. You plug in a negative 1 in here, that goes positive, divided by negative, positive divided by negative is negative, so this is negative 1. Same thing happens on the next one. You have something divided by itself, but that absolute value makes the numerator positive, and so you end up again with negative 1. Now, if you're having trouble seeing what I'm doing, on your paper, actually physically write these in. Actually input a negative 1 and simplify it, and you'll see what I'm talking about. For the last one, same thing. You have the same number on top and bottom, except that absolute value makes the numerator positive, so this is negative 1. And again, we have a strong pattern that's emerging. This is coming to negative 1, or it's converging to negative 1. So I'm going to continue with my graph. Down here in negative land, we come over like this. And so the reason I'm including the visual is to connect it to what we did in our first lesson with visual limits. Here we can see that as we approach the next value of 0, we don't have any kind of convergence. And so because these two don't match, for our initial limit, we're going to say it doesn't exist. Remember, we can only pick 1. So this is the exact same thing as looking at the table. We needed the two patterns to say the exact same thing, or the limit does not exist. Okay? Let's add a little bit more vocabulary to that. So we say that limits either converge or diverge, and I'm sort of exaggerating the way I'm saying it. We say converge or diverge. not converge. But the idea is if it converges, convergence means they're coming together. The two sides are coming to the same number. That's when we have a numerical answer. A diverging limit or a divergent limit is when the two sides don't come together. Diverging means to go apart, so when they're not coming together, when they're coming to different places, we say that it's divergence. That's some language that'll be popping up in the future, especially if you take more math classes beyond this one. Okay, we'll do another example, make sure we're getting the hang of it. So again, very similar. I've got the initial limit, and then I have just the left and right-handed limits sitting down here. So we can use these two to figure out the limit as we're approaching from both sides. And we're going to do the exact same process. We're going to pick some x values and some y, and then we're going to figure out what the y values are. So let's try it with here. I'm going to do the right-handed limit first. I'll actually annotate it this time as right hand. And so we'll start with x equals 1. 1 divided by 1 is 1. So y equals 1. Okay, let's try another one. I'm going to get closer and closer with my x value to 0 now. So if I try x equals 0.1. 1 divided by 0.1 should be 10. Okay, so they're getting bigger. Let's go a little bit closer. X equals 0.01. I'm going by orders of magnitude here. And so now I get y equals 100. Okay, bigger, bigger, bigger. Is there an obvious pattern? I mean, with the way I've picked these x values, sure. Yeah, these are getting 10 times bigger every time. But if I keep doing this, I can keep adding a 0 in front of it. I can keep sliding the decimal place over 1 all day, and I'm still not going to get to 0. And this number, this y value, it's just going to keep growing and growing and growing. And so this is going to grow infinitely large. They get really, really big. Okay, so that's infinite. Let's look at the left-hand limit. On this one, we'll pick the same symmetric numbers again. So x equals -1, x equals -0.1, and x equals -0.01. And we can see it's going to basically be the same thing, it's just flipped over the x-axis, because now we have a positive number divided by a -1. So instead of 1, we're going to get -1, we're going to get y equals -10, and y equals -100. And so where are these headed? Well, they're getting really, really big, but they're doing it in the negative direction, so we're going to put negative infinity there. And so if one of them is going to positive infinity, one of them is going to negative infinity, you might say, well, hey, they're both going to infinity. But they're going to different infinities. Since they don't match, we're going to say this does not exist. And by the way, as a side note, technically, these limits don't exist either, because those aren't numbers. And in the definition of a limit, it has to equal L, some number. It's not a concept. However, for assessment purposes, if it's infinite or negative infinite, that's what I want you to write. Do not write does not exist. And the reason for that for class is you're showing a lot more understanding if you use this to explain why the limit doesn't exist and why the limit doesn't exist. Okay, that's going to make a lot more sense. And it's going to demonstrate on an exam that you're not guessing. So that's a good thing. Okay. So why does that have that behavior? Well, here's the graph. You may remember this reciprocal function. We've got our curve there, and as we get close, as we approach 0 on this side, this is going up, that's the positive infinity. As we get closer and closer to 0, tracing from the left, it's going down, 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 down to negative infinity. Okay, so that's why that's happening. Okay, we'll talk a minute about continuity. And we've got a lovely, lovely piecewise function here. And just to start, all we're interested to know, are they continuous? And so remember that basic definition. Can we draw the function without lifting up our pen at all? And we've dealt with piecewise functions, like where we'd come and we'd put the open circle and then we have the dot. But notice, in order to draw that, I had to lift up my finger. So drawing up here, lift to bring it down. So if it's continuous, what that means is it might look something like this. Maybe we've got some open circle, and then the other part of the function, the other piece, fills that in and continues it onward. So we're going to learn an algebraic trick to test for that. So the way we're going to do that is two things. We're first going to ask the question, is each piece continuous? Okay, so what that looks like is this. I'm going to look at my first piece. I'm going to try to identify what that is. That's a quadratic. I know that quadratics look like parabolas, and all parabolas are continuous. Okay, first piece checks out. Second piece, it's also a parabola. Awesome. So it checks out as well. So we've satisfied this, the pieces are continuous. The other thing we then have to test is, do we have continuity at the overlap point? So where we hit 2 on an x value, we switch from this piece to that piece of the function. Is it continuous at that point? So let me write that out. Is it continuous? Okay, and I put points, I pluralize it, because a lot of times if you have 3 pieces, you're going to have more than one overlap point. Okay, and the way we test that is to just plug in the overlap point and see what happens. So let's try it. So I'm actually going to plug in a 2 here, and I realize with that symbol right there that technically we're not supposed to be able to plug it in. But remember, that's kind of the idea of what a limit is. That value doesn't actually have to be in the domain. It could be a discontinuity. Totally fine. We're allowed to plug it in with our understanding that it's a limit. And so let's do that. So we plug in a 2 here. I get 2 squared minus 4 times 2 plus 6. Let's simplify that out. 2 squared is 4 minus 8 plus 6, and we get 2 when we do that. Okay, that's the first piece. And now we need to test the second one. So we're going to see what we get out of this. And if the y values match, then yeah, this thing is continuous. If the y values don't, that tells us we have a discontinuity there. Let's plug in the 2 down here and see what happens. I've got negative 2 squared plus 4 times 2 minus 2. Be careful with your negative here. 2 squared is 4, so that's a negative 4 plus 8 minus 2, and that's also 2. Get 2, 2. So the answer to our question, is it continuous? Yeah, it is. So there's our answer, yes. And of course, you know the drill, you do have to show the work. Okay, we're going to talk a little bit now about horizontal asymptotes, which we learned last year, and how those connect to limits as x approaches infinity. And I want to give you the notation for it first. Okay, so I want you to focus right here. You're going to want to have this in the notes. X is approaching infinity. Everything else looks the same. And by and large, these are the exact same thing as horizontal asymptotes, and we're going to solve them with the same method. So we're going to do a brief intro. We're going to talk about a method for dealing with them when you have a rational function, and then we'll be done for the day. Okay, so we're going to treat this at first just like any other limit. We're going to see if we can actually plug in infinity. Now, warning, danger, you're not actually allowed to plug infinities in. We're breaking a rule of math right here, okay? And that's something we're going to do in calculus. Because we understand the rules of math well enough, we're able to understand the implications of breaking the rules, and we're able to be careful with that so that we don't get into trouble. So we are going to break this rule, and we're going to carefully interpret what that means and how that's useful, because breaking the rules actually will be very useful for us. Okay, so we're going to plug in an infinity. What I'm going to write should melt the board because it's not technically legitimate, but here we go. 1 divided by infinity plus 1. It's kind of tricky to divide by infinity, but we can think about it though. Like, imagine a story problem where you had a pizza and you had to feed an infinite number of people. How much pizza can each person have? Well, unfortunately, there are a finite number of molecules in a pizza, and so you can't even give a molecule to everybody. You can't even give an atom to everybody if you split it, because there's a finite number of those in a pizza. And so this becomes 0. You have 1 chopped into an infinite number of pieces. Those pieces end up having no size. And so what we have then is 0 plus 1, and that equals 1. And so the way we're going to do this with rational functions, we're going to use the blowout method. I've got the details of it over here. You probably remember this exact same method with the exact same name from when we learned how to find horizontal asymptotes of these same types of rational functions. I'm going to review it really quickly here. We're going to do a couple of examples, and then you can get off to practicing a little bit. So first things first, kill off the smaller, weaker powers of the numerator. Looks like my biggest exponent's 3, so everything else is gone. Kill off the smaller, weaker powers of the denominator. I have a 3, so everything else is gone. And then we're going to simplify, cancel what we can, and off we go. So I'm going to have limit as x approaches infinity. Let's simplify this down. X cubed divided by x cubed totally cancels out. 3 divided by 6 is 1/2. Where are you going to plug in the infinity? Nowhere. There's no variable anymore. So this limit as x approaches infinity doesn't really do anything anymore. And so what we have is just 1/2. Now be careful. The blowout method is only good for two things, so don't just apply it randomly. The only things it's good for is finding horizontal asymptotes and finding limits as x approaches infinity of rational functions. When I say rational function, I mean something that's a fraction, and it works best actually if it has polynomials in it. So be really, really careful. We don't apply this to all limits, only when you see infinity right there. Okay, so we're going to try these, and then we're going to look at some visuals of them. You may want to pause the video and try these on your own before watching the video and continuing. Okay, with these we're going to follow the same method, so we're going to cancel off all the smaller powers, and we're going to simplify. So limit as x approaches infinity of, let's see, 9 divided by 3 is 3, and x squared divided by x cubed is 1 over x, and so I get 3 over x. Plug in the infinity, I get 3 divided by infinity, and if you take 3 and chop it into infinitely many pieces, they have no size. That is 0. And I've prepared a little bit of a visual here. So take a look. This is what it is. Remember, with asymptotes and with infinite limits, that behavior only applies when the x values are really, really big and really, really negatively big. So yeah, right in here, it's crossing that horizontal asymptote. That's okay, because we're really close to the origin. But when we get way out here, you can see the function, it's getting closer, 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 closer. It's converging on 0. Okay, let's go to the next one. Okay, giving this one a try, we're going to cross off all the smaller, weaker powers. So we got a 2 there, 1 and 0 are gone. First power, so the constant is gone. Let's do some simplifying. We've got limit as x approaches infinity of 5/2 x. Okay, plugging in our infinity, we get 5/2 infinity. So what happens when you take something infinitely big and you multiply it by 5 over 2? I guess you have 5 over 2 infinities, but the question is that bigger? And as it turns out, it's not. We could do a video on infinity another day, but think about it this way. Even numbers, odd numbers, whole numbers, there's the same amount of all of those. And I know it seems like you take the evens and the odds and put them together and that would be more total numbers, but there's an infinite supply no matter how you slice that up. Those are actually the same size infinity. So when you double infinity or triple infinity, it still is just infinite. Which brings up another question, because I told you a minute ago that this was not only an infinite limit, but it's also a horizontal asymptote. So what does it mean like if you have an infinitely large horizontal asymptote? It means there isn't one at all. And the reason there isn't one at all is because this goes up, 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 and away. Okay? And so sometimes they won't have an asymptote. It is a rational function, but there is no horizontal asymptote on it. That's our video for today. I hope you enjoyed. Hope you have a good time with your assignment. Make sure that you're looking over the key or the mark scheme on the back with all the full work solutions. And if you don't understand the exercises, make sure you annotate every step if you weren't able to do them yourself. And if you're having trouble with annotations, bring that to class and we will discuss that together. See you next time.